All right, so linearization. If f is differentiable at x equals a, so some value of a, then the equation of the tangent line, L of x, so we're using L to identify it's a linear approximation, is f of a plus f prime of a times x minus a. Defines the linearization of f at a. The approximation f of x is approximately the linearization of L of x is a standard linear approximation of f at a. The point x equals a is the center of the approximation. So one of the things I do want to point out to you guys on this one here, that this is no different than doing a tangent line. When we use linearization, is we're using something that's close to a number to get to another number. And that's all we're using this for. So if you were to take this apart, this would be your y value. This would be your y1, f of a. This is your derivative, which is your slope. And then the x minus a, x minus your whatever that x value that got you this y value. So watch for this while we're doing these. So finding linearization, find the linearization of f of x equals cosine of x at x equals pi over 2. Then use it to approximate cosine of 1.75 without a calculator. So they're giving you the graph. They're going, here it is. So we got our cosine curve here, pi over 2. We can see what's going on, and we're going to form the linearization for it. So on this one here, we need our x and y value. So f of x is cosine of x. F at pi over 2 gives us cosine at pi over 2, which is equal to 0. So there's our y value. F prime of x is equal to negative sine of x, which makes sense, it's going to be a negative slope. So f prime at pi over 2 is equal to negative sine of pi over 2, which is going to give us negative 1. Sine at pi over 2 is 1, the negative becomes negative. So our linearization is f of a plus f prime of a times x minus a. This is giving us our linearization approximation. Now you can only use this if it's fairly close to the number that you're trying to use to begin with. So f of a is going to be 0 plus f prime at a, which is negative 1, times x minus pi over 2. So our linearization formula will be negative x plus pi over 2. Okay, 0 doesn't mean anything, and I distribute the negative. Now, there's our linearization formula. And at pi over 2, they're asking us now to use that to identify what cosine of 1.75 is. So the linearization at 1.75 equals negative 1.75 plus pi over 2. If you don't like the negative first, you put pi over 2 minus 1.75, wherever it's going to be. That's your value, and that's an exact value. Since they said no calculators, you're leaving it as such. And we're done. This is all we had to do. So I give you another one. It says find the linearization of f of x when equaling the tangent of x at x equals pi. Now keep in mind that pi is approximately 3.14, because I'm going to add to this problem. So on this one here, we're going, okay, so f of x equals tangent of x. F at pi gives us tangent of pi, and tangent of pi again is 0. F prime of x, tangent is secant squared. So f prime at pi equals secant squared. of pi. Secant squared of pi is -1, but this is going to be -1 squared, which is 1. So our linearization is f of a plus f prime at a times x minus whatever that a value is. And this is your a value. So we get f of a is 0 plus 1 times x minus pi. So our linearization for tangent at pi is equal to x minus pi. Now I said we were going to, this is all we're looking for, this is all they're asking you to do, but what we're going to do is we're going to estimate if at a equals 3, or x equals 3, whatever you want to call it. So L at 3 would be 3 minus whatever pi is. And I used 3 because I knew it was close to pi. Now, is this an exact value? No, but it's very, very close. So that's all I did, is I just used to give you the, don't forget this is something we're doing idea. Okay, so I threw another one in here for you guys to try again with a different one. Find the linearization of f of x at x equals 0. So f of x is a natural log of x plus 1, and f of 0 would be the natural log of 0 plus 1, or natural log of 1, and the natural log of 1 is equal to 0. Now let's do derivative. F prime of x. F prime of x is u prime over u, so 1 over x plus 1. So f prime at 0 is 1 over 0 plus 1, or 1. I'm going to get some nice numbers out of this one. So our linearization is going to be, again, f of a plus f prime at a times x minus a. So f of a was 0, so 0 plus f prime is 1, x minus 0. So your linearization function here is going to be just x, because everything else canceled out. So at this point, what we can do is figure out the linear approximation. Using the linear approximation, we have 0, so we can use like 0.1, 0.01. We can get our values from there, and it'll be very, very quick. Simple problem. Okay, I was going to stop here, but I decided to go ahead and continue on with this section because we're only not even 10 minutes into our thing. So let's talk differentials. Let y equals f of x be a differential function. The differential dx is an independent variable. So the differential dy is dy equals f prime of x times dx. This here is something important to know. We're going to do chapter number 4 in the homework together, and that's going to be one that you'll see because they have you do linearization approximation, and then they have you doing it with differentials as well. Okay, so on this one here, find the differential dy and evaluate dy for the given value of x and dx. So we have y equals x to the 5th plus 2x. Well, dy dx would be 5x to the 4th plus 2. But we want just dy, so we're going to multiply both sides by dx. So we get dy equals 5x to the 4th plus 2 dx. And now we can plug everything in. So dy equals 5 times 1 to the 4th plus 2 times 0.01. So 1 to the 4th power is still 1, so 1 times 5 is 5, 5 plus 2 is 7. So this is 7 times 0.01. So dy is equal to 0.07. And it's still giving us that same little bit of information. Okay, so a couple more problems to try. Get a trig one in there, get one with implicit differentiation in there so you can get it all done. Find the differential dy and evaluate dy for the given value of x and dx. So y equals sine of 3x, so dy dx is equal to 3 cosine of 3x. And if I move the dx over, I get dy equals 3 cosine of 3x dx. And now what we can do is plug everything in and get the actual value of y. So it says find the differential dy. There, done. Now evaluate. So dy equals 3 cosine of 3 pi times negative 0.02. So that gives us 3 times, and cosine at 3 pi is the same as cosine at pi, so it's negative 1 times negative 0.02. So we have negative 3 times negative 0.02. So dy equals 0.06. There's our dy value. Okay, this one a little bit more because we have our implicit differentiation going on here, so we have to take care of that. So this one's going to be easy, x and y, so derivative of x is 1, and derivative of y is dy dx equals, and we have to do this guy, so we're going to go to the side, product rule, x times y. So if u equals x, then u prime equals 1, v equals y, so v prime equals dy dx. Okay, and it's u prime v plus v prime u. Multiply this way, we get just y plus, and then multiply this way, we get x dy dx. So I'm going to move this x dy dx to this side, to the left, and I'm going to take the 1 and move it to the right. So subtract 1, I get dy dx equals y minus 1 plus x dy dx. And now I'm going to subtract the x dy dx. Subtract it from this side. And we get dy dx minus x dy dx equals y minus 1. We're almost there. We've got to factor out our dy dx. So we have dy dx is equal to, times 1 minus x is equal to y minus 1. Divide both sides by 1 minus x. And we get dy dx equals y minus 1 over 1 minus x. So just dy equals y minus 1 over 1 minus x times dx. Now notice we have a y value here, and if we go back up to our problem, they never gave us a y value. Up here they only gave us x equals 2. So I'm going to do a little bit more side work over here. I'm going to plug in 2 for x and solve for y. So I have x plus 2 equals 2x. I put in y. Let me try that one again. Erase. I'm putting x in for 2 in for x. So I get 2 plus y equals 2y. There we go. Subtract y, and I get 2 equals y. 2 minus 1, 1. So there I have my y value. X is 2, y is 2, dx is 0.05. So plug everything in that we know, so we get dy equals 2 minus 1 over 1 minus 2 times, I already forgot if it's positive or negative, 0, times 0.05. This is going to give me negative 1. 2 minus 1 is 1. 1 minus 2 is negative 1. Negative 1. So dy in the end is going to equal negative 0.05. And there you have it. That one was much longer. I get it. That was much longer, so we'll make sure that we get that one in class. In class, if we're running out of time, I'll leave this first one for you guys. Okay, so differential estimate of change. Let f of x be differential at x equals a. The approximate change in the value of f when x changes from a to a plus dx is df equals f prime of a dx. So it's basically what we were doing. What you were seeing was a change going from, like on the one for pi, let's look at the ones we just did, is going from pi to, and taking 0.02 off. That was a change of dy. And the same thing with the 2, and so from 0.05, it's the same as, we're looking at how does it change if we go from 2 to 2.05. Okay, so that's what this is just telling you. It's still the same stuff. So now they're looking at going, okay, now let's just put it more into application. The radius of a circle increases from 5 to 5.1. Use dA to estimate the increase in the circle's area A. So they're not giving us anything. We have to now look for this. So our A, which is really, first of all, area of a circle, pi r squared. So we need to know what r is, and we need to know what dr is. Well, r is 5. That's the same as your A value. And the difference between the two is your dr. So this is going to be 0.1. So if A equals pi r squared, then dr is going to equal 2 pi r. Or in other words, dA is equal to 2 pi r dr. And now we can plug everything in. So dA is equal to 2 pi, r value is 5, dr value is 0.1. So 2 times 5 is 10. We get 10 times 0.1 pi. And this is just going to move the decimal over here on 1. So 10 times 1/10 is the same as 10 divided by 10. So the change in the area is pi. Okay, and because it's derivative, it's going to be, we'll get what we've used for our measurement. Radius of a circle increases, so area is squared, so it's meter squared per meter. Okay, so the area is changing in pi meters squared as the radius is changing in meters. So when it goes to just from 5 to 5.1, that's how much it's changing. Okay, so this would be one for you guys to try on your own. I probably won't do this one in class, but I'll go ahead and do it in here so you guys have it, because everything's the same. All I did was change numbers. Area equals pi r squared. So dA dr is equal to 2 pi r, or in other words, dA is equal to 2 pi r dr. And this time our R value is 10. We can write in there, meters. And our dr is 0.1 meters. So plug everything in. dA equals 2 times pi times 10 times 0.1. These two are going to cancel out, just like they did the last problem, 10 divided by 10. So this is going to be dA equals 2 pi meters squared per meter. Says estimate the increase, so really it's just meters squared because we multiply these two, so not really meters squared per meter. But as that is opening up, that's what's happening. Okay, and then in class we're going to do number 4 on the worksheet. I put this on here so I don't forget that we're going to do that. All right, well, 21 minutes for this video, not too terribly bad. So good luck. Hopefully you guys do well on this.